Hi, welcome back to Integrated Science. I'm Ms. Sparks, and we're jumping into our new unit, which has to do with energy. And I like to think this unit right here really sets us up for the rest of the year with understanding how energy is moved through micro and macro systems. So today we're mostly going to focus in on our work and our power and how we can describe those two pieces of information in regards to motion, which we talked about last unit with Newton's 3 laws of motion with action and reaction, balanced and unbalanced, and then how how mass and acceleration can cause objects to move. And that's where we're kind of heading back to. How can we look at the mass of an object and in what direction is it moving with in regards to a force? And so we're going to practice those two today with our work and power and then get into our energy a little bit more. So grab a sheet of paper, we're going to take some notes, and then we're going to practice just what work and power kind of look like. So first off, just kind of talking a little bit about the idea in general. What is the physical meaning behind work? So you probably hear that term and you're probably like, oh, it's me going to a job, or I have lots of work to do in my integrated science class, whatever that may be. So it's kind of the same idea. It's just that we are looking at how an object is being applied a force and what is the distance that it's moving. So here's me and my cup of coffee. You know, I love my coffee. And so if we think about it, I just picked this up off of the table or my desk that I'm sitting at. And so we have energy that is moving through the system, and I'm applying a force to this cup as I move it up and down, or I can even move it closer to my mouth, further away, closer. I'm applying some type of force that is being moved in a distance. Now it's only the arm length that I have, so it's not going very far, but there is a distance that is the cup is moving, and then as well as there's a force. My body has muscles in them that might not be the strongest, but there are muscles in there, and I'm able to apply a force by contracting and thinking about like, oh, I need to move my arm, and so my body goes through all these little electrical impulses and does it for us. And so that is work. My body is doing work. We can look at it in several different ways too. Our bodies are a great example of simple machines that are always doing work. Your body is digesting food possibly right now, which is doing work. It's moving things through a system. Your heart is a great example of doing work. We want it to do work. If it wasn't doing work, you wouldn't be sitting here. So as long as it's pumping, it is causing your body to take blood and move it through your veins, through a system. So it's multiplying the force. It's pushing energy through, causing your blood to go to different parts of our circulatory system. And so therefore your body is doing work. So each system, even within our body, is actually doing that. So we could look at our skeletal system, we could look at our muscular system, our circulatory system, even our nervous system. All of them are doing different types of work where there's a force being applied and there's something that is moving a distance depending on what it is. Some of it is more tangible to be able to see than others. So work. Our equation for work is force times distance. And so we're going to be using this equation to kind of help us solve. So I'm going to write my T-chart over here, because that's really important. My marker just died on me. So let me get another one. It's that time of year, I guess, when all my markers start giving out on me. Ooh, this pretty pink one works just well, though. All right. So one big important thing that we're going to be discussing is that the force has to be applied to the direction in which the object is moving in order for this to be work. So once again, meaning that if I'm picking up and I'm moving my marker around, that my force is being pushed upward and the marker is being moved upward. So therefore work is being done. The force must be applied in the direction of the object's motion. Even if I let this drop to the ground, there's a force being acted upon the marker, gravity, which is pushing the object down towards the ground. So hopefully you remember that special number in which gravity is always working on objects here on Earth at 9.8 meters per second squared. That's a number that, once again, it's going to come up and kind of, I don't want to say haunt us, but we're going to be using it. So two different things to kind of realize with work. The first one is work is zero when an object is not moving. So object at rest stays at rest. There's no motion being applied. There's no force being applied. So it's a balance. It is staying at zero. But in order for an object to be doing work, we want unbalanced forces. So we are looking for what is the energy that is moving through. And so our unit of measure for work is joules. And we will record that with a J. And we'll actually use this quite a bit because work also has a big connection to kinetic and potential energy. And that's where we're kind of heading in the next couple of days here. So how do we find the kinetic and potential energy of an object, and how much work is it doing as it moves through those two energy types? We can measure joules two different ways. One is by taking the force and multiplying it by the distance, which is what we're going to practice with mostly here. However, sometimes we can take the mass and the acceleration too, and so we'll talk about that kind of as we move through both of them. So let's practice one. So it says, imagine a father is playing with his daughter by lifting her repeatedly in the air. How much work does he do with each lift? So he's just kind of tossing her up in the air, tossing her up in the air. When he lifts her 2 meters, our 2 meters is our distance, and exerts an average force of 190. So 190 newtons. So here is our T chart. Work equals force times distance. So we're just going to plug right into the equation. X equals 190 newtons times 2 meters. And when we do that, double check my math, it's been a day. I get 380 joules. So there's my work. So you can kind of see it plugged in there. So our T chart, W, we don't know. We don't know our work. That's what it's asking, how much work. Our force is 190 and our distance is 2 meters. So we're just going to plug those two in and solve. I think that's what those are saying down there. Perfect. Let's look at another one. So this one here says a man pushes a crate, and I'm going to erase my T chart as I'm trying to read there. Double tasking doesn't always work. There we go. All right, a man pushes a crate along a factory floor by exerting a force of 55 newtons. So the force is 55 newtons. And he is pushing the box or the crate at a distance of 4 meters. So once again, here's our T chart. Work, we don't know. Force is 55 times 4. So we're just going to plug that into the equation. X equals 55 newtons times 4 meters. And 55 times 4 is 220 joules. So our answer would be B. Once again, just plugging it in, looking at our work and also looking at what is the distance that is being applied. Power is piggybacking right off of work. So once we can find work, we can find the power of an object. Kind of like what we've been doing with our labs is that if you can find speed, you can find acceleration. If you can find acceleration, you can find force. And now we're going to take that even a few steps further. How can we find work and power, and then how does that apply to kinetic and potential energy? So work is the relationship between work and power, where power is the rate at which work is being done. So think about like if you've ever gone to like the gym or worked on maybe like an elliptical, a treadmill or something, is that the more power you put into it, the more faster the machine is going to kind of go and do things. This is the same idea, is that it's the rate at which work is done and how much work is done in a given amount of time. Meaning that we want to know what is in order to find power, we need to know what is the work and how long did it take to do so. So I always think of like, this is a great example of like cars. Once again, horsepower is that idea of like how much energy is moving through a car in order for it to be moving at a certain rate. Power is measured in watts. So you've probably heard that term before with the light bulbs. So, and I always think, well, of course, you need power, you need energy, and for a light bulb to go on and off. And so it's the same idea. Energy is being brought to the light bulb. When you flip the switch on, the connection is made that allows that energy to flow and light up the light bulb, whether it's an older light bulb where it's lighting up the resistor, the little metal that is running through it, or if it's one of our more newer LED lights, how that gas energy is lit up too. So power is the rate at which work is being completed. So once again, we measure that in watts, and 1 watt equals 1 joule per second. Our work divided by our time. And so let's practice the power. So once again, work equals force times distance. Power is work divided by time. I'm going to leave that right there for us. And let's look at this question. An elevator, lifting an elevator 18 meters takes 100 kilojoules. If doing so takes 20 seconds, what is the average power during the elevator is? Let me start over. What is the average power of the elevator during this process? Sorry, that was really hard. So let's look at what we're trying to figure out here. So a couple of different things. Once we do see that we have our given pieces of information. So let's write out our T-chart, power, work, and time. And we can see the question, what is the average power? So that's what we're solving for. So that's our variable. We can see that the elevator is lifted 18 meters. That's a piece of information that we don't really need. It's extra. We don't need it for what we're being asked to solve here. It does take 20 seconds, so that's our time. And it takes 100 kilojoules. And I'm just going to leave it in kilojoules. So all we have to do is take 100 and divide it by 20. And when you do that, you get 5. And so once again, we have 5, and that's going to be W for watts. So kind of you can see how it's all set up. We've got work at 100 kilojoules. Our time is 20 seconds. And when we divide 100 by 20, we get 5 watts. So 5 watts. And if you think about that, that's really small, because most of even our light bulbs are like 60, 40 watts and so forth. So there's just a formula on how to write that. And we will continue on with work and power, as we are going to put your bodies to the test and figure out how much work you can do and what kind of power is running through your system. So hopefully this was helpful. We're going to continue on talking about this and then how this is connected to kinetic and potential energy. Bye.